Hello everyone, in this video lecture we are going to talk about the photoelectric effect, and this photoelectric effect provides the best convincing evidence to prove that light is particle-like. Photoelectric effect was first observed by Heinrich Hertz in the year 1887, and further the experiment was carried out by Holwach and Leonard. When the classical wave theory could not explain the photoelectric effect, Albert Einstein developed Planck's theory and built the concept of energy quantization, that is energy is discrete, and with the photon theory he could explain the photoelectric effect theoretically, and this won him the Nobel Prize in the year 1921. So what is photoelectric effect? So when a surface of a solid, metal, non-metal, liquid or gas is illuminated by electromagnetic radiations, the electrons which are bound to the atoms or loosely bound to the atoms by some binding energy are emitted from the surface, and this phenomena is known as photoelectric effect, and the emitted electrons are called the photoelectrons. So one of the known applications of photoelectric effect is the solar cell, where the energy is converted to the electrical energy. So we know that most of the metals emit photoelectrons by UV rays, whereas there are certain metals, for example the alkali metals, where we know the cesium, potassium, sodium, they are able to show the photoelectric effect even with the visible lights. One thing to mention here, that not to be confused with the thermal emission, because that is completely different from the photoelectric effect. So this is the experimental setup for photoelectric effect to occur. There is an electric discharge tube holding a cathode and an anode, and are connected by a battery cell and an ammeter. So initially the ammeter does not show any non-zero value of current, but the moment cathode is illuminated by UV rays, ammeter shows a deflection, which implies that there is a current flow in the circuit. So the current, which is denoted by the small I, has been observed as a function of incident light frequency nu, incident light intensity capital I, and the potential difference between the cathode and anode, which is denoted by capital V. Now the experimental observations are the following. The non-zero current is often even with zero potential, as you can see here in the picture, where the plot is for the current versus potential for different intensities of light, for example I, 2I and 3I and so on. So here, even if the potential is zero, the currents are non-zero for various intensities of lights, and whatever the intensities of lights are, there is a certain negative potential, which is minus V0, where the current vanishes and is called the stopping potential, and is independent of the intensity of incident lights. So as the potential increases, the current also increases and saturates after a certain potential, and for every intensity of light the saturation of currents are different, and we see that the saturation value of the current increases with the increasing intensity of light. Then in the next observation, it was found that when the intensity is constant, the stopping potential is a function of frequency, and the stopping potential is more when the incident light frequency is more. For example, for light with frequency nu1, the stopping potential is minus V01. For nu2 it is minus V02, and we see that the frequency nu3 is larger than nu2, again larger than nu1. So we see that higher the frequency, higher is the energy of the incident light, and higher is the stopping potential. So you see here that the name stopping is justified, because this is an amount of potential which is required to stop electrons from to come out from any surface. That is, electrons maximum velocity will be 0, so that not a single electron is able to move out from the surface. And this can be written as the following, where the maximum kinetic energy of electron is E times V0, where E is the electron charge and the stopping potential V0, which is a function of frequency. So now this is a plot of maximum kinetic energy of electron versus frequency, and the plot could be same for the stopping potential versus frequency also, because we know that the kinetic energy of electron is related to the stopping potential. So here we see that whatever the energy of the radiation is, there is always a threshold frequency nu0 for the emission to take place. So in the plot we see that below nu0 there is no emission, and as the frequency is above nu0, the kinetic energy of electron increases linearly with nu. And based on the material properties, different material has different cutoff frequency. For example, nu01, nu02, nu03, so on. For the alkali metals, for example, cesium, sodium and calcium, and so on. So in this plot it is reflected that different alkali metals has different cutoff frequency, and one remarkable fact is that the slopes for all the surfaces are same, and turns out to be the Planck's constant, which is h. So we see that none of the photoelectric effect observations are in the favor of classical wave theory, because according to classical wave theory, photoelectric effect should occur at any frequency, and emission of electron would be proportional to the intensity of light. So when light incidents on a surface, electron should wait enough to gain sufficient amount of energy to come out from the surface. However, it has been observed that the photoelectric effect is an instantaneous phenomena and is frequency dependent. Only the rate of the electron emission is proportional to the intensity of light. Therefore, we see that it is not possible to explain the photoelectric effect from the classical ground, and therefore one has to accept the particle nature of light. Then from the experimental observations, Einstein realized that photoelectric effect can be understood only with the Planck's hypothesis, that is energy is quantized. So then he explained the photoelectric effect on the basis of photon electron interaction. So if light is composed of discrete particles, the particles are called the photons, and where each photon carries an energy h nu, where h is the Planck's constant and nu is the frequency of light. So when light with energy h nu incidents on a surface, the energy is transferred to the electrons, which are bound or partially bound to the electrons of the atoms, and the electrons they leave the surface after gaining enough kinetic energy from the incident light. Therefore, from the conservation of energy, energy conservation principle, we can write the following equation, where h nu is the incident energy, which is equal to the potential, which is denoted by phi, plus the kinetic energy, which is half me v square, which is the maximum velocity of electron, and me is the mass of the electron. So here the phi is the potential, which is basically the work function, and this is the minimum energy which is needed to make the electron free from the atoms. And this work function phi turns out to be h times nu 0. In fact, from this plot for the linear curve, one can write the maximum kinetic energy of electron as h times nu minus nu 0, where h is the slope of this curve, and h nu 0, that is minus h nu 0, is the constant shift from the origin. The equation, this equation is nothing but the famous equation of photoelectric equation of Einstein. And remember that the work function, which is phi, that depends on the material properties. So every material has its own work function due to different ionization potential. So now what we can say, that if energy of light which is moving with velocity c is mc square, and the light with a frequency nu, if the photon energy can be written as h nu, then if we combine these two relations, then we can get the photon momentum, because photon has rest mass m0 as 0, so the whole energy of photon is dynamic only. And then if we convert the wavelength to the wave vector or wave number, then we can write the photon momentum p vector as h cross k vector, and this k cross h cross or h bar is nothing but h by 2 pi, and this k is the wave vector or wave number, as I said. So thus it can be concluded from all these facts that light is a wave and a collection of particles too. Hence the dual nature of light is proved. Okay, so that's all. Thank you.